Hi, welcome to 19th session on group theory. This session will deal with the celebrated Lagrange's theorem and you give some applications of Lagrange's theorem. So let us get started. So let G be a group, H is a subgroup of G, then we define left cosets. Fix an element A in G, then AH is a set of elements of the form A times H, where H varies over H. Okay, in set theoretic notation, this is the set of element G in G, so that there is in H, so that G is of the form A times H. Okay, this is what you should learn, because whenever I say there is an X in this, what does it mean? It means I should be able to find some H, so that this X I should be able to write A times H. Okay, just by looking at this, people will not realize what is given. Okay. So what did we prove these things? We proved a lot of things yesterday. We proved that AH is H if only if A belong to H. The way we proved that was AH equal to BH if and only if A inverse B and B inverse A, they are all in H. Okay. And next we proved that if B belong to AH, then AH is same as BH. And we also said given two cosets AH and BH, okay, so one of the two, for exactly one and only one happens, and only one of the following holds. That is, only one of the following is true. Which one? Either AH is BH or AH intersection BH is empty. Okay, this is very crucial for what we are going to do. Let us know. We are given two cosets AH and BH, and exactly one of them must be true. What are the two possibilities? That is, AH equal to BH or AH intersection BH is empty. There is no common element at all. This is what we want to prove. Is that clear? Okay. Now let's prove it. Suppose given AH and BH, suppose AH equal to BH, then it's okay. We have proved it. Suppose AH is not, then I want to prove this is empty. Okay. Suppose it's not empty. That means there is a C here, which is in this. But C belong to AH, that means AH is same as CH. And similarly, C belong to BH, that means CH is same as BH. These two things put together imply AH equal to BH. Is that clear? Yeah. So let me review the proof. Okay, what did I prove? Given two cosets AH and BH, okay, if AH intersection BH is empty, then nothing to prove. Okay, I have to show then AH, okay, intersection BH is, suppose, okay, if AH intersection BH is not empty, then I want to claim AH equal to BH, right? So what did I do? Take a C in common element, therefore C belong to AH, but one of the properties says AH is, the coset AH is same as coset BH, CH. Similarly, C belong to BH, Therefore, the cosets CH and BH are the same. And hence, the cosets AH and BH are the same. So we proved it, right? So suppose C is the set of cosets of H in G. Okay. Then what I have proved, given two cosets AH and BH, these are set of cosets. You understand this? Right. So I claim this is a partition. What do I mean by that? Okay. So let us recall set theory. X is a set, assume it's a non-empty, and suppose A, okay, is a family. Script A is a family. Okay, a family of subsets of H. Then when do I say A is a partition of X? If two things should happen. If X must be union union A in script A. Now again foundations. Okay, and I partly reviewed this when I proved intersection of subgroups is a subgroups. Okay, so this is one of the reasons you should follow my lectures systematically. Whenever you find something difficult in the book or your classroom, you come only for that part in my video, you may not get any insight. You may even get more confused. Okay, so it's always good to see from the first video. If you know it very well, okay, just to fast forward it, but please go through it, because there are a lot of things which are not done in the class which are done, which I do in this series. Okay, so let us go back. So that means given any x, that is given any x in X, there exists an A in script A such that X belongs to A. And that is the one thing. Second thing, this is the first condition. Second condition is given A and B in the script A, then either A equal to B or A intersection B is empty. That means, okay, that they given any two distinct element, that is given any two distinct elements A, B in script A intersection B is empty. Okay, then we call it a partition. What is the picture? The picture goes something like this. This may be my X, okay, and this may be my partition. These are maybe this one, this may be my partition. Right, the union is X and any two members do not intersect. Therefore, we want to show G is union of C, where C is a coset. That is very clear given, because you give me any G in G, okay, then GH is a coset, right? Therefore, GH belongs to C. See, for example, GH may go as some AH or some CH, I don't care, but they are all the same set. Do you understand that? Okay, these are the things which BSc students may have difficulty. Okay, this may be my GH, but I must have listed it as AH, but these are the same. You understand? Right. So G is this, and this is a disjoint union. Okay, Pero is disjoint union. Okay, that is because given any two cosets, their intersection is distinct coset, their intersection is empty. Please understand. Again, if you have difficulty, let me just look at a special case. Okay, in case of difficulty, assume, okay, G is finite. Therefore H is also finite, and the number of cosets will be what? Okay, suppose my G is G1 to Gn, identity will be here. Okay, don't worry. Okay, what are all the cosets are JH. But what we know is, okay, there are not n cosets. Because remember, my G is Z, my H is NZ, where n is a natural number greater than or equal to 2. Then we found out the number of cosets are only finite. Right? Even though for each m in Z, I have a coset m plus nz. Okay, but finally this mz is same as r plus nz, where m is some qn plus r, where 0 less than or equal to r less than n minus 1. You understand? Therefore, when we say the set of cosets, we are looking at only set of distinct cosets. Right? Therefore, there may exist, let me call some elements gi1, gik, so that, okay, gi1h, gi2h, gikh. These are all the distinct cosets. See, I'm just thinking like a BSc student. Okay, many times set theory is now done very carefully. So these kinds of things are very vague for many BSc students. My earnest suggestion, advice is watch the foundation videos and again watch it with some of your friends. Okay, and that's why I took a lot of pain to explain the beginner's difficulty. If you are already matured, okay, you could have fast forwarded. Therefore, G is okay. C in script C. Script C is a set of distinct cosets. Okay, and this is, therefore this C is a partition. Let us look at some examples. Right? Again, let's look at G equal to this. My H is NZ. Okay. What is the C as? CZ is, okay, R plus NZ, where 0 less than or equal to R, less than or equal to N minus 1. You see, right? Therefore, union R plus NZ as R from 0 to N minus 1. This is all of Z. Because give me any integer m, by division algorithm m is nq plus r, where 0 less than or equal to r less than or equal to n minus 1. Right? Are you following? Therefore, m plus nz is same as r plus nz as we saw earlier. And these are the disjoint. This is, therefore the union is okay and their pair is disjoint, because given any m, there exists a unique remainder r. That is what uniqueness part of the division algorithm tells us. Again, see this. Why one has to learn elementary number theory very carefully? Okay. Our course structure, the syllabus, curriculum are exactly very haphazard. Okay. And they want to teach too many things and the basics are not very thoroughly done. Please understand how many times you have to be careful. Okay. Now second example, let us look at R2 and our H was x-axis. Okay, what are the cosets? We saw the cosets are lines parallel to y equal to some c. Okay, as you can see that, therefore R2 is pairwise disjoint union of of lines parallel to x-axis, which is a group. This is H. This is my, okay, 0C plus H. Okay, this is what you have seen. And the third example, what we saw was G equal to GLNR. My H was SLNR. That is set of determinant. This is with determinant 1. Matrix with determinant equal to 1. Right? And what did you see? Start with any A in H. Yesterday I used in the last section A in G. Now I will use small a so that my life will be easy. Now A is in a matrix, n cross n matrix. Okay? Invertible matrix. Therefore, what is AH? It is set of matrices whose determinant is determinant of A. That's it. And determinant of A, where is it vary? Belong to R star because non-zero. Right? So, my G is union of, I can write it as, let us say, CR, where R is in R star. And what is CR? CR is set of all G in G, so that determinant of G equal to R. Okay. Now you can see this is again a partition. So pause, review, proceed. Okay. It again, as a way of encouraging, I am just saying, in classroom these things will not be taken to in such a detail. Such examples will not be looked at. So if you think it's not important for me for exam, then you will suffer in case you want to choose mathematics as your profession later. Okay, learn these things very well. So what have we done? So what have we done? Summary. If H is a subgroup of G, then G is union of, okay, is partition into the distinct coset classes, distinct cosets of H in G. Right? Now there is something very interesting. Let us look at some AH and BH, two cosets. Let me record AH and H. Okay? This is the coset EH. Right? Now I want to say there is an obvious bijection of H into AH. Namely, H going to AH. Okay? I claim this is a bijection. That is actually this is our lambda A. Remember, it's nothing other than restriction of lambda A. We know lambda is already a bijection. Right? And what is lambda A of H? That is A of H. Right? And therefore, okay, lambda A restricted to H is a bijection. Okay, pause, review, proceed. If you want directly, okay, suppose H1, AH1 equal to AH2, then multiplying both sides on the left by A inverse, I get H1 equal to H2. Therefore, this map is 1, 1. And is it on to, because start with any in A in AH, then there exists a H in H, so that X equal to AH. Therefore, right, I take, if you want to say, let us say H naught. Okay, then for H naught goes to A times H naught, which is X. Therefore, this map is on to. So, what have we shown? So, any coset AH is in bijection with H. That is, intuitively in AH there are as many elements as in H. Right? Okay. Now we are through. Okay. Let us just have a digression. Okay. Suppose X is a set and X is partition. Okay. Let us say I equal to 1 to n, and X is a finite set, n elements. Okay. And it is a partition into M. Okay. A1, A2, AM. These are all subsets of X. This is a partition. Right? One usually writes by putting a dot or a square. Yeah. Okay. Now assume further A equal to number of elements in A is AJ for 1 less than equal to I less than equal to M. Say each is equal to D. Right? Then what is number of elements in X? Okay. This is the number of elements in A1 plus number of elements in AM, but each is D. Therefore it is MD. Right? That means the number of elements in I divides the number of elements in X. Okay, pause, review, proceed. Now we are ready for the famous Lagrange's theorem. I will state it, okay, and I will say how it follows from whatever is seen, but I will give again a complete proof, because we did lot of in-depth analysis. Sometimes you may get bewildered, you may get intimidated, so I will give how simple the theorem is. Okay. Let G be a finite group. Let H be a subgroup. Then the number of elements in H divides the number of elements in G. That is, if D equal to number of elements in H, notice that H is a subset of G, G is finite, therefore H is also finite, and N is the number of elements in G, then D divides N. Okay. How does the proof follow? Right? Let A1H, AKH be the distinct cosets. Cosets of H in G. Right? Notice that G is finite. Therefore, the number of cosets will be, just as a digression, G is finite. Therefore, any coset is of this form. Therefore, the number of cosets will be at most number of elements in G. Do you understand that? Yeah. As A varies over, I get a coset, but to some for the cosets AH and BH and CH may coincide, but at most 3. Therefore, the number of cosets is finite. So let us look at all the distinct cosets, call this A. Then what we know is G is union of AI H, where I equal to 1 to M. Right? And this is the disjoint union. Therefore, number of elements in G is same as number of elements in A1H plus AMH. But we know number of elements in A1H is same as number of elements in H and plus number of elements in H. Okay. But that is, there are how many times? M times D. Therefore, D divides N. Okay, that's it. Proof is over. Is the idea clear? Okay, forget about my digression to various other things. What are the proof then? Start with the subgroup and then look at the cosets. Then if I form the distinct, collect the distinct cosets of H and G, then they form a partition of G. That is G equal to union of AIH, where AIH are distinct cosets. Right? Now if G is finite, okay, the number of elements in G equal to summation of number of elements in AI of H. But what we know, the number of elements in AI of H is same as the number of elements in H. That's it. Proof is over. Yeah? Please go through that. Enjoy the proof. Then now we will arrive at some of the very important applications. The first one is very non-trivial. Suppose G is a finite group and A is an element of G. Right? Can the order of A be infinite? Because if the order of A is infinite, then what will happen? A to the power n, as n varies over z, all of them will be distinct. That means it will be infinite set, which is a subset of a finite set G. So it cannot. Therefore, order of element A should be finite. The surprise is it's a divisor of the order of the group. In fact, in many of the exams earlier, I was almost ready to use this, but then I had to contain myself that I have not proved Lagrange's theorem yet. Okay, let us give a proof. That's the most important and the first application in my opinion. Okay, applications. One, let G be finite. A is an element of G. Then order of A is finite and order of A divides the number of elements in G. As I said, whenever see, unfortunately one also call the number of elements in G also order of G. Okay, so is that clear to you? Now as I said, okay, this is finite, we already know. If order of A is infinite, then the cyclic subgroup generated by A is A to the power n, nz is contained in G. Since order of A is infinite, all these elements are distinct. That is, this set is infinite set. So that's a contradiction. Therefore, order of A must be finite. Next, let's look at, see now I want to say order of A divides G, order of G, then I want to use Lagrange's theorem. If I want to use Lagrange's theorem, what is that I need? I need a subgroup, then only I can apply. Order of the subgroup divides order of G. So what subgroup will I consider here? Yes, look at H to be the cyclic subgroup generated by A. Okay. Then this is again another thing. Now, how many elements are there? Notice that H is a subset of G, therefore it must be finite. How many elements are there? That we have seen, right? When you define order of an element, we said the number of elements in the cyclic group generated by A equal to the order of A, right? Therefore, norm which divides this by Lagrange, but this is same as order of A, therefore order of A divides order of G. This is a very powerful result, right? You see that the subtlety of the argument, various small things we have to use, right? Namely, order of A is same as number of elements in the cyclic group generated by A, right? Very good. The next thing, this is a very powerful result. I just want to give applications for this application. Okay, let's look at it. Suppose I have a group, okay, let's say order 12. Okay, I want to know whether there exists an element of order 8 in G. Right? If such an element A exists, then what should happen? Order of A, which is 8, should divide order of G, which is 12. That is, 8 should be a divisor of 12. That is not possible. Therefore, no such element exists. Okay, this is application 1A. That is application. First A application of application 1. Then let's look at application 2. Suppose I want to know whether there exists, okay, a group homomorphism F from, let us say, Z7 into a group of order 24. Right? So, or suppose there exists such an F exists. There may be many, choose one. Right? Now, let us look at what are the things we are going to use. Now, I know kernel of F is a subgroup of Z7. Let us assume the order is, okay, is K. Therefore, K must be a divisor of 7. What is K? K is the number of elements in kernel. Right? K must be a divisor of 7. Therefore, what are the possibilities? K must be 1 or 7. Is that clear? Suppose K is 7. What does it mean? Okay. Kernel, this is a subgroup of Z7. This has 7 element. This also has 7 element. That means kernel of F equal to Z7. That means for all elements X in Z7, what we have, Fx must be identity. That means F is trivial homomorphism. Right? Suppose K equal to 1. If K is 1, that means kernel is trivial. Consists of only the identity element. Therefore, F is 1, 1. Since F is 1, 1, now let's look at F of Z7. Okay. This will have how many elements? 7 elements. And what we know, this is a subgroup of what? G. And how many elements are there in G? 24. Now this is the subgroup of this group. Therefore, number of elements of this, namely 7, must divide 24. That is absurd. Therefore, what does it mean? That means K equal to 1 cannot happen. Therefore, K equal to 1 cannot happen. Therefore, that means K must be 7. If K is 7, what do you have? F is trivial homomorphism. So, what have we shown? We have shown the only homomorphism F from Z7 to G, where G is a group of order 24, is the trivial homomorphism. Did you see how many times we applied just for fun? I applied Lagrange's theorem because kernel of F is a subgroup of Z7 and image of F is a subgroup of G, right? Etc. etc. Just enjoy this kind of example, right? Because most often what I find is if you say I have a group of order 24, does there exist a subgroup order 9? The student will say 9 does not divide. That kind of easy examples is what they usually say. But this is slightly twisted, but they are again easy applications, right? Okay. Now let's go to the next application. Suppose I have A4. Do you remember A4? Alternating, that is subgroup of even permutation. In S4. Okay, one usually calls alternating group. Right? So, what is the number of elements in A4? 12. Because remember, mod n is half of mod Sn, which is half of n factorial. Right? Therefore, these are 2 elements. Now let me look at a subgroup generated by some 3 cycles. I'm just writing something, whatever comes to my mind. You can try with something else. Okay. This is a subgroup generated by this. What does that mean? This is the smallest subgroup containing the cycles 1, 2, 3 and 1, 2, 4. Right? Okay. Now how do I find it? Okay, I want to identify. Okay, identify H. This example I just thought of just for fun. Okay, let us see whether something interesting happens. Now, since let me call it alpha and beta. The alpha is 1, 2, 3. Therefore, alpha squared must also be in H. But what is alpha squared? Alpha squared is 1 goes to 2 and 2 goes to 3. Therefore, 1 goes to 3 and 2 goes to 3 and 3 goes to 1. Therefore, 2 goes to 3. Sorry, 2 goes to 1 and 3. 3 goes to 1, 1 goes to 2. Therefore, 2. This I know. Therefore, it is same 1, 3. 1 goes to 3, 3 goes to 2 and 2 goes to 1. Therefore, it is cycle 1, 3, 2. And beta is 1, 2, 4. Therefore, beta squared should also be in H. What is beta squared? So, 1 goes to 2, 2 goes to 4. Therefore, 1 goes to 4. Right? And then 4 goes to 1 and 1 goes to 2. Therefore, 4 goes to 2. And 2 goes to 4, 4 goes to 1, therefore 4 goes, therefore it's a cycle. Right? Now notice that already there are 1, 2, 3, 4. These cycles are all different. Alpha, beta, alpha square, beta square are already different. And this identity element is also must be in H. There are already 5 elements in H. Right? Now what are the possibilities of order of H? Okay, it must be a divisor of 12. That means it must be 2, 1, 3, 4, 6 or 12. Right? These are the thing, because 12 is what? 2 squared into 3. So whatever possibilities I have will be there. Right? Okay. I hope I got all of them correct. Okay. So there are already 5 elements. Okay. Now let us look at, since alpha is there, let us look at alpha beta. Alpha beta is 1, 2, 3, 1, 2, 4. Therefore it's 1 goes to 2, 2 goes to 3, 1 goes to 3, and 2 goes to 4, and 4 goes to 4. Therefore 2 goes to 4, and 3 goes to 3, 3 goes to 1, and therefore 1, 3. Therefore I do not fill it. That is 1, 3 and 2, 4. Do you understand this? And what is beta alpha? Beta alpha is 1, 2, 4, 1, 2, 3. Therefore 1 goes to 2, 2 goes to 4, and 4 goes to 4, 4 goes to 1. Therefore it must be etc. Therefore it must be cycle 1, 4 and 2, 3. Right? Now all these elements must be in H. And notice that, okay, identity alpha, beta, alpha squared, alpha beta, beta alpha, they are all distinct 7 elements. And they are all in H. Therefore H must be all of A4. Right? Because the only possible orders of number of elements in this is ruled out. Therefore either 6 or 12, but I already found 7 elements, therefore 6 also not allowed, therefore only 12 elements. Isn't it fun? Yeah, good. Right, let us look at one more. Now the example which I want to give is a group theoretic proof of a well-known theorem in number theory. I don't remember the exact name. There it goes under Wilson's, Fermat, or Euler's. I don't remember such things. Okay, please forgive me. Look at their textbook. You will find it. Okay, so it's a theorem which I am going to do that. Let us do it. Now let's look at G equal to Z mod P, okay, under multiplication, right, where P is a prime. Assume P is greater than equal to 3 for that. Okay, let us see. Now, what are the number of elements in G? There are P minus 1 elements, because it is consists of all integers which are prime to P, which between 1 and P minus 1, right? So, and 0 is excluded, non-zero element, but each one of them is a prime, therefore P minus 1 element, right? Yeah, right. Before going, see, sorry, let's look at, suppose G is a finite group, A is an element of G, then we define Y of A is a divisor of number of elements in G, which is n, right? Therefore, notice that if, therefore n I can write as some m times Y of A, right? Therefore, it follows that A to the power n is always identity for every A in G. Are you following? Whatever be the order, I don't care, but that is going to be a divisor of n, therefore I can write n as a multiple of O of A. Therefore, this is A m into order, right? This is A d power m, therefore it's identity. Okay, this is the corollary which I forgot. This is a very important corollary. Okay, pause, review, proceed. Now come back to the earlier example. So I have ZP star, right? Now to start A to be any one of the elements 1 to P minus 1, then A to the power P minus 1 must be 1 in ZP star as group elements. But in terms of number theory, what does it mean? When or two elements are equal, there, if they are congruent modulo, A to the power P minus 1 is congruent to 1 mod P. Okay, this is in group theory. This is in number theory. Right? So if I multiply by A both sides, it is going to be A to the power P is congruent to A mod P. For all A. Now this is including of 0 to 1 to P minus 1. Because for 0 also is a correct statement. Okay. So this is known by some theorem, somebody's theorem. This is by known as somebody else's theorem. Okay, I'm sorry. I don't recall, but okay, I think it's a Wilson. I'm not very sure. Wilson or Fermat. I think it's Wilson. Okay. These are the applications of Lagrange's theorem. Okay. We proved Lagrange's theorem. We also give some non-trivial application. There are a lot more applications, but as I keep saying, I cannot do all, right? It's not a comprehensive course. I want to give things which will make you comfortable and confident. That's why I do a lot of silly examples so that you become comfortable how to work with those objects, not only abstract theory. Okay, I hope you enjoyed. We will meet again.